Counting outcomes and theoretical probability. Don't get scared by the big words. It'll make a lot more sense. It's a lot more simple than theoretical probability. So we're counting outcomes. And theoretical probability. I'll move my hand in a second. I only put prob because that's as far as I can get. If that doesn't fit, just have like counting outcomes. So write as much of that as you can. You can.
Theoretical. How do you spell?
Theoretical is Theoretical.
How do you spell probability?
Probability is PROBABILITY. So go ahead and flip on over to page 38, or not 38, 36 for our Unit 6 objectives. It's Unit 5 and 6. They've merged. So on page 36, we're going to go ahead and write. We're going to be able to use a tree diagram and the counting principle to count the possible choices. It'll make sense in the notes. Yes. So use a tree diagram and the counting principle to count possible choices. And secondly, we're going to find theoretical probability by counting outcomes.
By counting outcomes?
Yeah. So find theoretical probability by counting outcomes. Once you've gotten that, flip it on over to page 40. So once again, we're going to use tree diagrams and the counting principle to count possible choices and find theoretical probability by counting outcomes.
When's our next class?
Not this week or next week.
Thank you.
So flip on over to page 40, and at the top, once again, write counting outcomes and theoretical probability. So counting outcomes and theoretical probability. where I go to school. Mid-America. Okay, so we're going to talk about something called the counting principle. So the counting principle, we're going to use this when we're trying to find the possible choices that we have. We're going to use X and Y because we do not know. This is a formula we can use to find the total possible outcomes. So if there are X choices, of 1 and Y choices of another, then there are X times Y choices. So once again, we're using X and Y because we are unsure at this point how many different choices, one or another options we're going to have. So we're going to go through an example and we'll show you how we can use this. So X and Y could be any number at this point, but in our example we'll have a specific number. So our example is Hawker Grove is selling shirts. There are 2 color options. Red and black. With those red and black t-shirts, they're offered in men's and women's fit. And they're also offered in long sleeve and short sleeve. The question is, how many shirt options are there? And to answer that, we will use what is called a tree diagram, and then we'll also use the counting principle after that. So using what's called a tree diagram, Sachenauer thought it more looked like roots, but we're going to use what's called a tree diagram. For the sake of space, red shirts are going to be R's, black shirts are going to be B's, men's and women's M and W, long and short L and S, for the sake of space in our notes. So we have one option of a red shirt and one option of a black shirt. With those red and black shirts, we have the option of, what do we have? Men's and women's for both red and black. each men's and women's shirts, what are their options? You can have a long sleeve shirt or a short sleeve shirt. That's red or black, men's and women's. So you could get a red men's shirt that's long sleeve, or you can get a red women's shirt that's short sleeve, or just following each of the lines to different locations, we could have a red women's long sleeve or a black women's long sleeve. So how many options do we have across the bottom for a shirt? Colin? 6? So we have 8 options across the bottom. So that means we have 8 choices. So that's doing this using the tree diagram. What about if we use the counting principle? How do you think this would work? We had 2 options for shirt color, 2 options for gender, and 2 options for sleeve length. Up here we talked about if there are X choices of one and Y choices of another, we multiply X times Y. Cameron? In this case, it'd be 2 to the third, or 2 times 2 times 2, right? So we have X options, Y options, and Z options in this problem. So we have X times Y times Z in this problem, where X is shirt color, which we had 2. Y is gender, which we had 2, and Z is sleeve length, which we had 2. So what's 2 times 2 times 2? That'd be 8. So those are 2 ways to find the total number of choices that you have when given choices for different options. Does that make sense? We can use either of these. On the homework, it'll ask you to use sometimes the counting principle, sometimes drawing the tree. On your homeworks, you can make abbreviations or letters for the options, just like we had R and B, M and men's and women's, and then L and S. So, there's the counting principle and a tree diagram. Now we're going to talk about that theoretical probability. So when we're looking at theoretical probability, when we're thinking about theoretical probability, you'll probably see it written out like this as P of the event. So P of the event equals our theoretical probability. That's how you're gonna see it on your homework. So when we see this, it's gonna ask for a ratio or a percentage or a fraction. In the numerator, we're gonna have the number of favorable outcomes. So number of favorable events. So the events, it'll ask you a certain type of event, and and the numerator will be the number of favorable events that can happen. So what do you think we can place in the denominator? If it's the number of favorable events in the numerator, what should the denominator be, Luis? All the events. So the number of possible outcomes is our denominator. So number of possible. So we're going to look for the probability of an event. We're going to count the number that are favorable, put that in a fraction over the number of possible events. So let's take a look at an example of what that might look like. What is the probability of tossing a coin and both times that you toss it, it's tails? This is a theoretical problem, so let's work through it with the tree diagram and put it in our theoretical probability fraction. So what is the probability of tossing a coin and both times tails? Or you might see it something like P of 2 tails. So when flipping a coin, we have two options of it being heads or tails. So we're going to use another tree diagram, and we're going to use H for heads and T for tails. So the first flip, you flip to the coin, you either got heads or tails. So those are our options. So let's say you got heads the first time, you flip it again. You can get heads or you can get tails. Say you flipped it the first time and you got tails. Then you go ahead and flip it again and you can get heads or you can get tails. So now theoretically we flipped the coin 2 times. What's our theoretical probability of getting 2 tails? Colin? So there's 4 total possibilities, so we're going to put that where? In our fraction. Where are we going to put that? The denominator. So there's 4 possible options, and Colin, you got that how? So you counted each one of the ones at the bottom. So now, how many favorable events did we get to get 2 tails? Alexis? So we need to get 2 tails. Here we got heads. So there's no way we can get 2 tails here, right? Here we got tails and heads. That's not 2 tails. Here we got tails and tails. So how many times was that possible or favorable outcomes? 1. Because of the 4 second flips, there was only 1 time that it could be both times it flipped was tails. Does that make sense? So this is all theoretical. You could flip a coin a whole bunch of times, it could be heads a whole bunch in a row. But this is the theoretical aspect of it. In theory, it's heads or tails like that. Does that make sense? Okay, so now we're going to do another work, a little more work with theoretical probability. So we're going to look at our chances of winning the lottery. We'll work through an example problem to see what our probability of winning the lottery is. So what are the chances of winning the lottery? Okay, what are the chances of winning the lottery where the winning ticket has 6 numbers? So what are the chances of winning the lottery where the ticket, where the winning ticket has 6 numbers. In our case, there'll be 1-digit numbers, 6 different one-digit numbers. And let's say you bought 4 tickets. What is the probability that you have the winning ticket? So we have a lottery ticket number that has 6 digits, and we bought 4 of them. So thinking about this, how many options are there going to be for the first digit? The numbers can be 0 to 9. So we have 10 options for the first. For the second, still 0 through 9, we have 10. For the third, we'll have 10. Fourth, we'll have 10. Fifth, we'll have 10. And sixth, we'll have 10. So now we have 10 to the 6th power, or 10 times 10 times 10 times 10 times 10 times 10. So what does that equal? How many zeros are we going to have? It equals 1 million. How'd you get there so quick, Colin?
Because, well, you just got to count the zeros.
So we count the zeros and we put 1 in front of it. So we have 6 zeros. And we have 1 million. 1 million possible outcomes, right? Yeah, sorry. So now we have 1 million possible outcomes. And how many tickets did we buy?
4.
So what does that mean? Do we have... It's almost 1 in a million. So Chris says we have 4 and 100 or 1 million options, right? And then Colin, you went ahead and simplified that. How'd you simplify that? So we take 1 million divided by 4, and that equals 250,000. So what happens if we didn't know 4 went into 100 or 1 million? We can divide it by 2, get to 2 and 500,000, and divide that again. Where did we get the 4 from? Who wants to answer that question? Chris.
The number of tickets you bought.
So we bought 4 tickets. And that's how we have the 4 favorable options. So we have 4 possible options, 4 favorable times of winning the lottery.
That's really close to my guess. I think 1 in a million.
So if we continue to simplify that, we get 1. And as Colin said, 250,000th chance. Obviously, it's a lot smaller chance of winning the actual lottery. Jesus. Yeah. Good catch.
How'd you make it all the way down to the bottom?
Hmm? I decided to try to start writing bigger for you guys. That's all. You're welcome. Okay, so